Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about inelastic buckling theories of column. So far, we have discussed about spring bar models. As you can see from the right side, the member was considered rigid. The solution was based on a set of algebraic equations. From spring bar models, we migrated to Euler columns, where the member was considered as deformable, as you can see from the right-hand side picture. So the member was assumed to be perfectly straight before loading and obeys Hooke's law. We also defined what is known as effective length factor K for different boundary conditions. The solution was based on a set of differential equations. From Euler column, we went to columns with practical boundary conditions. Here, the boundary conditions are idealized as linear and rotational spring stiffness, as you can see from the right side. The solution was based on matrix method. So recall, for Euler columns, the critical load P critical is P critical equal to pi square EI by L square. Substituting I equal to AR square, we have P critical equal to pi square E into AR square divided by L square. We bring A to the left hand side, so we have P critical by A equal to pi square E into R square divided by L square, which is equal to pi square E divided by L by R the whole square. So P by A becomes sigma critical, which is equal to pi square E divided by L by R the whole square. So when we look at the stress strain curve of mild steel, as you can see here, the stress is in the y-axis and strain is the x-axis. We have 3 points: proportional limit, elastic limit, and yield point. We also have the ultimate strength D and the fracture or breaking point E. Here the point B corresponds to Fy and point D corresponds to F sub U. When sigma less than sigma y, the column is in elastic stage, which corresponds to elastic buckling. The assumption so far, the material behaves in a linear elastic manner which obeys Hooke's law. When the column is short, what happens? When the length of the column is short, the length decreases, the sigma critical increases, as you can see from the expression at the top. Then sigma critical is greater than F sub y. The column is no longer in elastic stage. It leads to what is known as inelastic buckling. The material behaves linear elastic as well as plastic after yield. Does the Euler equation holds good for inelastic buckling is the question that we need to answer. So inelastic buckling of columns. Till now, the assumptions were made such that the material obeys Hooke's law, valid below the proportional limit. So as you can see from the curve here, we have L by R as the slenderness ratio at the x-axis and sigma critical at the y-axis. We have an Euler curve, which is a parabolic curve, described as sigma critical equal to pi square E by L by R the whole square. Now there is a cutoff point, which is when sigma critical is equal to sigma y, it reaches the maximum strength of the material. So the point that is corresponding to that differentiate between a stocky column as well as a slender column. The one to the left is stocky column, which means that the column is shorter in length, and to the one to the right is a slender column where the length of the column is much longer, having a long or higher slenderness ratio. However, the axial stress of these stocky columns will exceed the proportional limit of the material before it reaches the Euler stress, which is sigma critical. The linear elastic analysis, which is Euler load, is therefore valid only for the slender column. Consequently, the results of elastic analysis are not valid for short or stocky columns. The buckling of short or stocky columns must be determined by considering the inelastic behavior. Failure criteria for columns. 1 is squashing. The number 2 is bifurcation buckling. Number 3 is first yield, basically onset of yielding. Number 4 is maximum strength or divergence of equilibrium. So within this, there are several theories that correspond to that. For squashing, we have stub column. For bifurcation buckling, we have Euler theory, tangent modulus. For first yield or onset of buckling, we have Perry's formula, secant formula. For maximum strength or divergence of equilibrium, we have Shanley's theory, von-Karman theory, and Batterman-Johnston theory. The ones that are highlighted in blue are the ones that we have already studied, and the ones that are in red are the ones that we will be discussing in the further classes. Before we go into other things, let's look at the historical development of the column buckling. In 1744, Leonhard Euler introduced the Euler formula, which is P critical equal to pi square EI by L square. He assumed that the formula can be used for both short as well as slender columns. In 19th century, the test results indicated that Euler formula is unconservative for short columns. Euler formula was discarded for a long period of time. Again in 1889, Two researchers, one is Engesser and Considere, stated that the Euler formula was valid but only for slender columns. So the Euler formula could be applied for short columns if constant modulus E is replaced by the effective modulus that depends on the magnitude of the stress at buckling. Engesser believed that tangent modulus will be the correct effective modulus and hence introduced the theory tangent modulus theory. Considere suggested that as a column begins to bend at the critical load, there is a possibility that stresses on the concave side increase in accordance with the tangent modulus and that stresses on the convex side decrease in accordance with the Young's modulus. So he introduced the concept called double modulus theory. Now in 1910, von Karman, the famous researcher, re-derived the double modulus theory, which was widely accepted throughout. So he came up with the concept of double or reduced modulus theory. And in 1947, Shanley, an engineer working at Lockheed Martin in the US, re-examined the mechanism of inelastic column behavior. He said that tangent modulus theory is correct and double modulus theory is wrong. So tangent modulus theory, double modulus theory, and there is Shanley's theory in between. So the tangent modulus theory underestimates the strength. The double modulus theory overestimates the strength. Shanley's theory is in between the two. So logically, it is correct. And for design purposes, it is better to use a tangent modulus theory. So the gist here is, initially, critical load of a perfect column is determined using small deflections. Then initial imperfections and finite deformations are introduced. Theoretical findings are used to develop design criteria for real engineering structures. So now let's talk about double modulus theory. For columns whose axial stress exceeds the proportional limit prior to buckling, the following assumptions were made. The column is initially perfectly straight and concentrically loaded. Both ends of the member are hinged. The deformations are small enough for the curvature to be approximated by y double dash. The same relation exists between bending stresses and bending strains as exists between stress and strain in simple tension and compression. Plane sections before bending remain plane after bending, hence longitudinal strains vary linearly as the distance from the neutral surface. The critical load is obtained by means of a concept of neutral equilibrium. That is, the critical load is defined as the axial load at which equilibrium is possible both in the original undeformed position and in an adjacent slightly bent configuration. This definition implies that the axial load remains constant as the member moves from the straight to the deformed position. Let us consider the column as follows. So you have a column which is axially loaded. The final deformed configuration of the member is reached by applying an axial force P to the initially straight column. Let the force increase until it reaches the critical load P critical and the member bends slightly while the axial force remains constant. So as you can see from the plot below, you have P delta, which is P is in the y-axis, the applied load, and delta is the lateral deformation. We can see that until it reaches the buckling load, nothing happens, there is no deformation. And once it reaches the buckling load, there is a sudden change and the lateral load keeps increasing. The slope is equal to 0 at buckling and delta P, there is no additional increase in load with increase in delta small delta, which this small delta represents the lateral deformation and the triangle delta indicates the small change. The axial stress sigma critical is equal to P critical by A that is present in the column when it begins to bend is assumed to be above the proportional limit sigma sub P of the material. So when you increase the load beyond sigma critical, the loading is governed by E sub T, which is the tangent modulus. However, when you unload it, it is governed by the Young's modulus E. So during bending, there occurs a small increase in the stress on the concave side of the column and a slight decrease in the stress on the convex side of the member. As you can see from the plot here, the inside face is concave, the outside face is convex. C1 and C2 represents the distance from the neutral axis towards the outside face and inside face respectively. And there is a point of consideration which is Z1 and Z2. The central line is Z. To the right is actually plus Z, to the left it is minus Z. At any point in the cross section, the total stress consists of a uniform axial stress and a variable bending stress. So the uniform axial stress is represented by sigma critical. The variable bending stress is represented by sigma 1 and sigma 2. Sigma 1 equal to E into epsilon 1. For unloading, E governs. sigma 2 equal to E sub t into epsilon 2. Here for loading E sub t governs. E sub t is the tangent modulus is the slope of the stress strain curve at sigma equal to sigma critical. Since deformations beyond the critical load are assumed to be infinitely small, bending stresses are very small compared to sigma critical, and the tangent modulus E sub t corresponding to sigma critical can be assumed to apply over the entire part of the cross section where the stress is increasing. Noting that the curvature d phi is the rate of change of slope, the bending strains epsilon 1 and epsilon 2 located at distances z1 and z2 from the neutral axis are pictorially represented by the following figures. So, tan d phi equal to minus epsilon 2 ds divided by minus z2, which implies epsilon 2 equal to z2 into d phi into ds. Here we are making the assumption as tan d phi equal to d phi for small deformations. Similarly, on the other side, we have tan d phi equal to epsilon 1 ds by z1, epsilon 1 equal to z1 into d phi by ds. The same small deformation theory is applied here as well. Substituting y double dash in place of d phi by ds, since an assumption of small deformations were made, epsilon 2 equal to z2 into y double dash, epsilon 1 equal to z1 into y double dash. Now, for equilibrium, it has been assumed that the axial load remains constant during bending. Therefore, condition number 1, the resultant of the tensile and compressive stresses due to bending must therefore vanish. Number 2, the bending stresses balance the externally applied moment m equal to py. Condition 1 indicates 0 to C1 sigma 1 dA plus 0 to C2 minus sigma 2 dA is equal to 0, where C1 is the distance from the neutral axis to the outside face and C2 is the distance from the neutral axis to the inside face, which is concave. This can be further simplified as 0 to C1 E into epsilon 1 into dA minus 0 to C2 E sub t into epsilon 2 into dA is equal to 0. This is given by the equation sigma 1 equal to E into epsilon 1 and sigma 2 equal to E sub t into epsilon 2. This again can be further simplified by using the formula epsilon 1 equal to z1 into y double dash and epsilon 2 equal to z2 into y double dash. When you substitute the same here, we have 0 to c1 e into z1 into y double dash dA minus 0 to c2 integral e sub t z2 into y double dash into dA is equal to 0. Introducing the notation q1 equal to 0 to c1 z1 into dA and q2 equal to integral of 0 to c2 z2 into dA, which is the first moment of inertia. So the above equation can be further simplified as e y double dash into q1 minus e sub t y double dash into q2 is equal to 0. So e q1 minus e sub t into q2 is equal to 0. We know that e is not equal to e sub t, which is the Young's modulus is not equal to the tangent modulus. Hence, q1 cannot be equal to q2. For the neutral axis to coincide with centroidal axis, q1 must be equal to q2. This implies that the neutral axis doesn't coincide with the centroidal axis. Now, the second equilibrium condition is that the bending stresses balance the externally applied moment m equal to py. So, the condition 2 gives 0 to c1 sigma 1 into dA, which is the force multiplied by the lever arm z1 plus 0 to c2 minus sigma 2 into dA, which is the force in the concave side multiplied by minus z2 plus py, which is the externally applied moment, should be equal to 0. This can be further simplified by substituting the values of sigma 1 and sigma 2. So, we have integral of 0 to c1 e into epsilon 1 z1 into dA plus integral of 0 to c2 et epsilon 2 z2 into dA plus the externally applied moment py is equal to 0. We know that again epsilon 1 equal to z1 into y double dash and epsilon 2 equal to z2 into y double dash. This further simplifies as integral of 0 to c1 e into z1 square y double dash dA plus integral of 0 to c2 e sub t z2 square y double dash dA plus py is equal to 0. Now we take ey double dash common. So we have ey double dash into integral of 0 to c1 z1 square dA plus e sub t into y double dash into integral of 0 to c2 z2 square dA plus py is equal to 0. Introducing the notation I1 equal to integral of 0 to c1 z1 square dA and I2 equal to integral of 0 to C2 Z2 square dA, which is the second moment of inertia. So we have E y double dash I1 plus E sub t y double dash I2 plus Py is equal to 0. So we take y double dash common, E I1 plus E sub t I2 plus Py is equal to 0. Introducing the notation, E sub r, which is the reduced modulus, is equal to E I1 plus E sub t I2 divided by I. So we have E sub r into I into y double dash plus Py is equal to 0. This is the differential equation for the bending of a column stressed into the inelastic range of the material. So in the inelastic range, E sub r into I into y double dash plus Py is equal to 0. So in the elastic range, Ei into y double dash plus Py is equal to 0. So both are identical except that the E is replaced by E sub r. So E sub r is the reduced modulus, which is less than the Young's modulus, and E sub r is given as Ei1 plus EtI2 divided by I. So ER depends on the stress strain characteristics of the material and on the shape of the cross section. Along the length of the column, E sub r is constant, that is, it is not a function of x. Therefore, the solution of the differential equation for inelastic range is same as that of the elastic range. PR critical is equal to pi square E sub r into I divided by L square, the critical load of an initially straight column whose axial stress exceeds the proportional limit prior to buckling. Since E sub r less than E, P sub r is always less than P. So PR critical is equal to pi square E sub r into I divided by L square. So sigma r critical is equal to pi square E sub r into AR square divided by AL square, which further simplifies as sigma r critical is equal to pi square E sub r divided by L by R the whole square. To determine the critical stress for a member, it is necessary to determine the reduced modulus E sub r. From condition 1, we have EQ1 minus E sub t Q2 is equal to 0. Q1 is given as integral of 0 to C1 Z1 into dA, and Q2 is given as integral of 0 to C2 Z2 into dA. So when we integrate it, we have Z1 square by 2. The lower limit is 0, the upper limit is C1 for Q1, which gives rise to C1 square by 2. And when we do the same for Q2, we have Z2 square by 2. The lower limit is 0, the upper limit is C2, which gives rise to C2 square by 2 is the value. So now we have E into C1 square by 2 minus E sub t into C2 square by 2 is equal to 0. So E C1 square minus E sub t C2 square is equal to 0. We have E C1 square equal to E sub t into C2 square. C1 and C2 are the distances from the neutral axis to the extreme fibers in the tension and compression. Noting that H is the depth of the cross section, we know that H equal to C1 plus C2. So this can be further simplified as E divided by E sub t equal to C2 square by C1 square, or the square root of E by E sub t is equal to C2 by C1. Now C2 equal to C1 into root of E by E sub t. So which gives rise to H equal to C1 plus C2, and instead of C2 we substitute C1 into root of E by E sub t. So we have H equal to C1 into 1 plus root of E by E sub t, which gives rise to the value of C1, which is equal to H divided by 1 plus root of E by E sub t. So C1 equal to H into root of E sub t divided by root of E sub t plus root of E. Now C2 equal to C1 into root of E by E sub t. So C2 equal to H into root of E sub t divided by root of E sub t plus root of E into root of E by E sub t. So C2 is equal to H into root of E divided by root of E sub t plus root of E. Now E sub r is equal to E I1 plus E sub t I2 divided by I. So I1 is given as 0 to C1 Z1 square into dA, and I2 is given as integral of 0 to C2 Z2 square into dA. So the first integral gives Z1 cube by 3, the lower limit is 0, the upper limit is C1, which gives the value C1 cube by 3, that is equal to 1 by 3 into H into root of E sub t divided by root of E sub t plus root of E the whole cube. Now the second integral gives rise to the value Z2 cube by 3, the lower limit is 0, the upper limit is C2. So we have C2 cube by 3, which is equal to 1 by 3 into h into root of e divided by e sub t plus root of e the whole cube. So substituting the above values of I1 and I2, we have ei1 plus e sub t I2 equal to e into bracket open 1/3 of h into root of e sub t divided by root of e sub t plus root e bracket close the whole cube plus e sub t into 1/3 of bracket open h into root of e divided by root of e sub t plus root of e the whole cube. This can be further simplified as ei1 plus e sub t I2 equal to 1 by 3 into h cube divided by root of e sub t plus root of e the whole cube into e into root of e sub t the whole cube plus e sub t into root of e the whole cube. Now the root of e sub t the whole cube can be expanded as e sub t into root of e sub t, and similarly root of e the whole cube can be expanded as e into root of e. When we do the same thing, we have the following equations below. Now we can take e and e sub t as common, and we have in the brackets root of e sub t plus root of e, which can be cancelled by the denominator. So we have the equation 1/3 e into e sub t into h cube divided by root of e sub t plus root of e the whole square. Now we also know that e sub r, the reduced modulus, is e into I1 plus e sub t into I2 divided by I, where e sub I1 plus e sub t I2 is equal to 1/3 e into e sub t into h cube divided by root of e sub t plus root of e the whole square. For a rectangular cross section, I equal to bh cube by 12, where h is the depth of the cross section and b is the width of the cross section, and which can be further simplified as I equal to h cube by 12 for unit width. Substituting the above in the equation, we have e sub r equal to 1/3 of e into e sub t into h cube divided by root of e sub t plus root of e the whole square whole divided by h cube by 12. This can be further simplified as e sub r equal to 4 into e sub t divided by root of e sub t plus root of e the whole square. Similarly, for an idealized cross section, e sub r is 2 into e sub t divided by root of e sub t plus root of e. Now, let's look at tangent modulus theory. For columns whose axial stress exceeds the proportional limit prior to buckling, the following assumptions were made. The column is initially perfectly straight and concentrically loaded. Both ends of the member are hinged. The deformations are small enough for the curvature to be approximated by y double dash. The same relation exists between bending stresses and bending strains as exists between stress and strain in a simple tension and compression. Plane sections before bending remain plane after bending, hence longitudinal strains vary linearly as the distance from the neutral axis. So this is very similar to the double modulus theory. So what is the difference between double modulus theory and tangent modulus theory? There is one important distinction. Recall, for double modulus theory, the axial load remains constant as the member moves from the straight to the deformed position, whereas in the tangent modulus theory, the axial load increases as the member moves from the straight to the deformed position instead of being constant. It also assumes that the increase in the average axial stress is greater than the decrease in the stress due to bending at the extreme fiber on the convex side of the member. Hence, no strain reversal takes place, which means that both of them are in compression, both the convex side and the concave side. The compressive stress increases at all points, and the tangent modulus governs the relation of stress to the strain for the entire cross section. Let us consider the column that is initially straight. The column remains straight until the axial load P equals to the critical load. Then the column moves from the straight position to a slightly bent configuration, and the axial load increases from P to P plus delta P. Here, the slope is not equal to 0 at buckling, and the delta P is greater than 0 with increasing delta. When we compare that with double modulus theory, we have the slope equal to 0 at buckling and delta P equal to 0 with increasing delta. Now, if you look at it, we have the stress strain plot where sigma P is the proportional limit and sigma critical is the critical buckling stress. Here, the E sub t, which is the tangent modulus, governs in this case. We have the straight form where the column is loaded by an axial force P, which is much less than the critical load, so there is no visible deformation. Now, when the load reaches P plus delta P, then we have the bent configuration. We can see the cross-section area. The dotted line represents the neutral axis. To the right is positive Z, to the left is negative Z. We have an uniform axial stress, sigma critical, that is acting, and we have a variable stress, that is delta sigma. So this is the forces that are acting due to the applied load. The deformations are given here. So we have a deformation as shown in the picture here. Noting that the curvature is the rate of change of slope, we have dphi by ds. This can be pictorially represented by the following figures here. So tan dphi is equal to minus delta epsilon ds divided by minus z. Assuming small deformations, we have delta epsilon is equal to z into dphi by ds. The assumption is tan dphi equal to dphi when the small deformations take place. Substituting y double dash in place of dphi by ds, since an assumption of small deformation was made, we have delta epsilon equal to z into y double dash, which indicates that delta sigma equal to E sub t into delta epsilon, which is equal to E sub t into z into y double dash. So we take the equilibrium here. We have the internal forces that are acting. We have integral of A into minus delta sigma into dA, which is the force. The lever arm is minus sigma plus the external force P into y plus. Now we have the equilibrium condition where we have the integral of A. Inside the brackets, we have minus into delta sigma into dA, which is the force that is acting, multiplied by the lever arm minus Z, which is the internal resistance. And the external resistance is given as P plus delta P into Y, which can again be split into Py plus delta P into Y, which is equal to 0. Since delta P is very small compared to P, it can be neglected. So we have this equation, integral of A into E sub t sigma y double dash into Z into dA plus Py is equal to 0. How did we get this? We are basically substituting. Instead of delta sigma, we have E sub t into Z into y double dash, which has been substituted. We can further simplify this equation, which gives rise to the value E sub t into y double dash integral of A into Z square dA plus Py is equal to 0. E sub t into y double dash plus Py is equal to 0, which is very similar to the Euler equation Ei into y double dash plus Py is equal to 0. So both are identical except that the E is replaced by E sub t, where E sub t is the tangent modulus, which is less than the reduced modulus, which again is less than the Young's modulus E. Therefore, the solution of the differential equation for the inelastic range is same as the plastic range. P sub t into critical is equal to pi square E sub t into I divided by L square. So P sub t critical equal to pi square E sub t into AR square divided by L square. So we have sigma t into critical is pi square E sub t divided by L by R the whole square. So let us look at the tangent modulus theory with an example. Consider a rectangular column of proof stress 350 MPa with Ramberg-Osgood stress strain curve. The strain at every point on the Ramberg-Osgood stress strain curve for the corresponding stress can be determined using the equation epsilon is equal to sigma by E plus 0.002 bracket open sigma by sigma at 0.2 proof stress the whole power n, where n is the Ramberg-Osgood parameter. The Ramberg-Osgood model parameters are given here. At proof stress sigma, 0.2, which is 0.2% proof stress, we have 350 MPa as the yield stress. The strain corresponding to yield stress is 0.00375. The ultimate stress is 450 MPa. The strain corresponding to the ultimate strain is equal to 0.10225. The Young's modulus is 200,000 MPa. The elongation is 10%. The strain at fracture is 0.1. The strain hardening component is 1 by n, which is given by the value 0.064242 and Ramberg-Osgood parameter n, which is given as 15.56625. These are the parameters that are given in the problem. Now, how to solve this problem? We plot the stress versus strain. Here we get the stress strain curve, and since it does not have a definite yield point, we have to go through the proof stress. So it is 0.2% strain. We draw a line parallel to the Young's modulus curve, and we hit a point. That point corresponds to the yield stress, which is 350 MPa, as you can see from the plot. Now to determine E sub t, so when we differentiate it, we have dou epsilon divided by dou sigma is equal to 1 by E plus 0.002 divided by sigma n at 0.2 proof stress multiplied by n into sigma power n minus 1, which can be further simplified by taking LCM. We have the equation on the right side. When we invert it, we get dou sigma by dou epsilon is equal to E divided by 1 plus 0.002 E divided by sigma power n at 0.2 and n into sigma power n minus 1. So this is the tangent modulus E sub t, which is given by this equation. Note, if a bilinear stress strain curve was used instead of Ramberg-Osgood model, the tangent modulus theory will yield the same values as Euler theory. Here, we plot the E values with respect to stress. We have three different E values. The lowest one is the tangent modulus, which is red in color, and then followed by the reduced modulus, which is intermediate, and then we have a bilinear curve. This indicates that the tangent modulus is less than the reduced modulus, which is less than the Young's modulus. So, tangent modulus theory, reduced modulus theory, Euler theory. What is the difference? Here, sigma t critical equal to pi square E sub t divided by KL by R the whole square. The reduced modulus gives you sigma r critical equal to pi square E sub r divided by KL by R the whole square. The Euler theory gives sigma critical equal to pi square E divided by KL by R the whole square. So, which gives rise to the differing values of slenderness ratios. So, KL by R critical with respect to tangent modulus is given as root of pi square E sub t divided by sigma t. And for reduced modulus, we have KL by R critical with respect to reduced modulus is equal to root of pi square E sub r divided by sigma t, where KL by R with respect to critical buckling load for Euler theory is equal to root of pi square E divided by sigma. So now when we plot the stress versus the slenderness, we see that the Euler curve is exactly the parabolic, whereas the tangent modulus theory and the reduced modulus theory differs after it reaches the critical slenderness ratio, which is given here, where the tangent modulus theory is the lowest value, followed by the reduced modulus theory, which is in between the tangent modulus theory as well as the Euler theory. With this one, we understand that the lowest modulus is the tangent modulus theory, which is very conservative for design applications. The reduced modulus theory appears to be correct, but however, it has its inherent flaws and cannot be used directly. The Euler theory is impractical because after it reaches the critical slenderness ratio, there has to be a change in the slope, which the Euler theory does not capture because Euler theory does not take into account the inelastic behavior of the columns. With this one, we would complete the theories of the column for tangent modulus theory as well as reduced modulus theory. We'll come back with more theories in the next class. Thank you very much.